Hello everyone, and welcome to part 2 of the Pong help session. In this part I'm going to be covering rough spots where people often get stuck or have trouble and have to come to the TAs for help. You can look on the screen for this lovely table of contents. If you don't see it, your annotations are turned off. So let's get started. There are two tricks to this part of the program: creating the delay and, unless you use printf, displaying the splash images that have been provided in pongimages.c. One of those images, called pong_image, is used already in new game event in a function LCD word image. However, opening the file where this image is stored shows us that pong_image is made up of uint16s and the 3, 2, 1, go are made up of uint8s. Word image will not work with uint8s, so you're going to have to use LCD bit image instead. The next hurdle is creating the delay. If you remember back to the dice lab, there was a function you could use called WDT delay. It's not hard to write a similar function, so let's go through the pseudocode together. We'll need a function, a global variable, and some code in the watchdog timer to do our timekeeping for us. The code in our watchdog and the global variable are provided already because Pong interrupts isn't a file we're supposed to change. But if we look at the code for the watchdog timer that blinks the green light in the Pong interrupts file, we can see that there's a global variable seconds that's incremented whenever a second passes. So let's write our delay function. We want to get the number of seconds in as a parameter, and then delay for that number of seconds. There's one trick with this. This process is triggered by a button press. So if the button is pressed at the end of a second interval, we may have a delay that's too short to see. Because of this, if we tell it to delay for 1 second, and we press the button right at the end of a second interval, we may not even notice the delay. It could look like it would skip the 3 in our 3, 2, 1, go. There are two ways to fix this. We can mess up the green light's timing a little bit, or we can mess up the 3's timing a little bit. We can mess up the green light by a few tenths of a second when this part of the code is run, or we can hardcode an extra second's delay into the 3, and we may have a variable delay time. If you tell it to delay for 1 second, it would definitely delay for 1 second, but then it may also delay for up to another second. The variable delay bugs me more than messing up the green light a little bit for this part, so I'm going to start out by resetting the watchdog timer second count variable. That way I know I'm going to get exactly how many seconds of delay as I have specified in the parameters. If you'd rather mess with the 3's timing than the green light's timing, you may just want to increment the parameter that was passed in. No matter which system you use, you'll want to reset the seconds variable to 0 for the easiest implementation. Now we know that the watchdog timer will increment the seconds variable for us, so all we have to do is test it. When it reaches the same value as our parameter, or if you've changed the value of the parameter to account for the time when it reaches your new value, we know that the correct amount of time has passed. We can then return from the function. The paddles and ball are made with C structs. Structs are similar in functionality to classes in C++ or Java. Structs are C's way of going about object-oriented programming. It's a theoretical object that's made up of several values. Only one paddle is created for us, but we can use it as a template to see how to create the second paddle. If we go to the pongevents.c file, we can look at the example code for how the first paddle is created. We can see that there's a function, newPaddle. It's given a number and right pot. That's associating it with the right potentiometer. All we have to do is say left pot when we're creating the left paddle. Now let's find out what that number does. If we go to the newPaddle function, we can see that that number is the x-coordinate of our paddle. We can go back to where we found the right paddle being created and create a left paddle. Now we've created the paddle, but we're not controlling it. We know from our systematic decomposition that the event ADCRead is supposed to move both the paddles, so let's go to that event. This function looks like it's meant to take in an arbitrary paddle as a parameter. We could edit this to take in 2 paddles and calculate the changes but it's way easier to just call the function for each paddle. It's actually called in pong.c, where it determines that it's supposed to do ADCRead event. ADCRead is then called with the right paddle, so all we have to do is call ADCRead with the left paddle. There's one last thing we need to do here. You can see that the right paddle is referenced because we create it in another file. Don't forget to reference your left paddle. The code you are given does not let the paddles reach the top and the bottom of the screen, so that's one of the things you have to change. The screen is 160 pixels high, and the potentiometers that we use to control the paddles have 1024 inputs. A mapping of 1 to 1 won't work because the paddle would go off the screen and stop being printed. You'll need to scale the potentiometer value down, and as long as you do this in one line, you won't need a double to store it. An important objective of this lab is to practice allocating memory on the heap for holding objects. In C, this is done with the malloc function. There's some very good example code on the website, including an example of how to malloc structs. This is supposed to go in your new paddle and new ball functions in Pong events.c. Just as in the example code, we'll make a paddle pointer, and then we'll assign our newly malloced object to that pointer, then use the provided syntax to initialize the elements of the new paddle. Our function is designed to return a pointer to a paddle, so at the end all we have to do is return the pointer we created at the beginning. The method for working with the ball is the same. The trick with allocating memory on the heap is that you have to remember to free it when you're done. Otherwise, you have what's called a memory leak. You are allocating more memory than you were releasing. If you remember back to the earlier labs, we sometimes did that with the stack and had stack overflows, so you know that it's a bad idea. Detecting collisions is always a bit of a challenge. Look at all the professionally made video games or their engines that don't always get it right. Fortunately for us, all we have to do is see if the bounds of a circle are interacting with the bounds of a rectangle, which is about as simple as it gets. Collisions are handled in the move ball event. We can easily get the x and y coordinates from the paddles and the ball by using this code. These coordinates are in the middle of the objects, so you have to account for the pixels between the two origin points. If the ball appears to be eating your paddle when it hits, the ball is getting further over than it should be. As the ball moves, it doesn't just draw the new ball, it erases the old one. So what it's doing is it's hitting your paddle, and then it's erasing the pixels where the ball was, but that's also overlapping with your paddle. So until you move the paddle and redraw it, it looks like it's had a bite taken out of it. The code for how the delta y, or for our purposes, the angle of reflection, should change when the ball hits the paddle is conveniently in the PowerPoint for the lab. The move ball event is affected by timer A, so there are two ways we could possibly make the ball move faster. We can make timer A interrupt more frequently so the ball moves more in the same amount of time, or we can change how far the ball moves. The second option is like cutting the frame rate. It looks horrible and it makes gameplay harder. It's also harder to implement. We'll just change timer A instead. If you look at the code that's supposed to become your new rally event, you can see these lines here that set a variable ball speed to a constant ball speed. It's a good naming convention until you say it aloud. The variable ball speed is the one you'll want to change. Tac row here is the counter timer A uses to see when it should interrupt. So if the ball speed variable is smaller, timer A will interrupt more often because it doesn't take as long to count down. However, the code for actually changing that variable needs to go in move ball event because the ball is supposed to speed up when it hits a paddle and reset at the beginning of a rally, which is what this is doing.